Welcome back. Today, we're going to be covering the product quotient and the adding/subtracting rule of derivatives. So, last time we went over the power rule, what happens when you multiply by a constant and when you take the derivative of a constant. Now, this time we're going to cover when it's multiple things being added or subtracted, multiplied, or divided. Okay? Now, before we start, quick note. Unfortunately, the word is not derivatize a function. It is differentiate. So the book has a chapter 3.3 called Differentiation Rules. Personally, I think derivatize sounds funnier, but oh well, right? So with that said, let's get to it. So we want to find the derivative of all this mumbo jumbo, right? With respect to x. Okay, well, last time we had one thing, we could do the power rule. And if you remember from limits, we had the limit x goes to a of f of x plus or minus g of x is the limit x goes to a f of x plus or minus the limit x goes to a g of x. Which just means we can break it from one big thing into a bunch of little things, right? And the same thing applies for derivatives. So let's do it. What's the derivative of 2 times x cubed? Well, the derivative of x cubed is 3x squared. And we double that. Then we subtract, what's the derivative of x squared? 2x times 6 plus, what's the derivative of x? Just 1. And the derivative of a constant is 0. So we get all this, right? We can simplify this down a bit. Beautiful, right? So now, for some extra practice, let's find the derivative at, let's say, x equals 1, just so it's easy to plug in. We get 6 times 1 squared minus 12 times 1 plus 4. 6 minus 12 is negative 6 plus 4, negative 2. Awesome. So this is the general derivative. This is the derivative evaluated at x equals 1. Okay. Now, there's going to be more practice for this, as it's a very common rule, but consider this other rule, right? We originally had this function. Now, you just have to trust me on this, but this function is equal to x minus 3 times 2x squared plus 4, right? If you don't trust me, multiply this out so that you get this. Or you can factor this and get this, right? So, let's differentiate the same thing with a different face. Oops. Right? Well, now we have these two different things being multiplied, right? It's a very ugly x. Well, we can't just do the derivative of this times the derivative of this. What we can instead do is this beautiful acronym that I learned when I was taught calculus was LDR plus RDL. So we have L is the left, DL is the derivative of the left. If you can guess, R is the right. And dr is the derivative of the right. Okay, well, let's see what we get. L equals x minus 3. We differentiate this to get dl, we get 1. right? R equals 2x squared plus 4. dr equals 4x. Okay, let's plug it into the formula. We get L times dr plus R dO. Okay, now let's prove that this is equivalent. Right, we get 4x squared, or shall not prove, minus 12x plus 2x squared plus 4, 6x squared minus 12x plus 4. Wow, that's a very, very bad 4. This was equivalent to when we did it via the adding and subtracting part. Now, what does all this look like in terms of some fancy math notation? For the adding and subtracting, it looks very similar, right? Oops, forgot to close the parentheses. You can just take it apart, do it individually, it's the same thing. For the product rule, I don't expect most people to actually use this notation. However, if you have two functions being multiplied, it's the left times the derivative of the right, plus the right times the derivative of the left, right? So now, with that said, let's do a practice problem. Find the derivative of x plus 2 times x cubed plus 5x. So, what is it? LDR plus RDL. Right? You can get the first two from the problem, and then you just got to differentiate them. Now put them in the formula. And you get this mumbo jumbo. If it's a multiple choice question on the AP test, you typically do have to simplify from here. If it's an FRQ though, you're good to go. So I'm going to take the FRQ route, which is a bit lazy, but that's okay. Now, thus far, we've only talked about polynomials, right? But I think we can agree there's plenty of functions that are not polynomials, right? For example, what's the derivative of sine of x? You don't know. Don't Google it. You don't know, right? Well, if you want to find it, you can do all of this. And if you want a good challenge, I recommend it. However, for the following functions, it's typically best to memorize. So the derivative of sine is cosine, and the derivative of cosine is negative sine. Using these two, you can derive every other trig derivative, which we will be doing in most likely the next video. But for right now, we're just going to memorize this. And that's what I do recommend for just these two functions specifically. So, we know the product rule. What about the quotient rule? Now we have something divided by something else. The quotient rule is a bit more annoying, but it's nice to still have. It is low d high minus high d low over low squared. High refers to the numerator, low refers to the denominator, d low, d high are their derivatives respectively. So high is x squared plus 3x minus 10. D high is 2x plus 3. Low is x cubed minus x minus 6. D low is 3x squared minus 1. You plug it into all of this mumbo jumbo, you get when you plug it into the formula, you get all this mumbo jumbo. I will not be simplifying this. I don't think you'll be expected to, unless something very nicely cancels out. So now, let me write it up in fancy math notation. Here is the quotient rule in this math notation. I also do not expect you to prefer this notation. It's very, very annoying looking. But yeah, now, let's move on to one final problem, putting to use the quotient rule in trig. So as a friendly reminder, from about, 10 minutes ago maybe, 5, something like that, we said the derivative of sine was cosine, and the derivative of cosine was negative sine. What about the derivative of tangent? Well, there is an answer that you could memorize, or we can derive it. So we want the derivative of sine x over cosine x, which is going to be low d high minus high d low over low squared, right? High d low, low d high, low cosine, d high, derivative of sine, cosine, minus high sine, derivative low, derivative of cosine is negative sine, over low squared, cosine squared, which is cosine squared of x plus sine squared of x divided by cosine squared of x. Now, this is where trig identities come into play. You do need to know this one off the back of your head. Sine squared plus cosine squared equals 1. So we get 1 over cosine squared of x, which is secant squared of x. 1 over cosine is secant, just for reference, right? So this is secant squared of x. Awesome. Now again, there is no practice problems for these because there's going to be one rule that puts it really all together and it's really nice to have. But for now, look at these problems over again. Start singing low D high, minus high D low over low squared LDR plus RDO. It'll come to you naturally. Remember the derivatives for sine and cosine, which I should probably circle just to emphasize, right? And this will come to you, be great. In the next video, I'm going to derive the derivatives of cotangent, cosecant, and secant, all right? So yeah, I'll be doing it using this, and thank you for watching. If this video was helpful, consider leaving a like. If it was not helpful, leave a comment as to how I can improve. I tend to read them. If it was really helpful, maybe consider subscribing. But yeah, otherwise, thank you for watching. See you next time.